My name is Jack Michael. This is Physics 2212, Lab 4 DC and RC Circuits. Introduction. The purpose of this lab is to use principles of current and energy conservation through the loop rule and steady state circuit. Predict and examine the behaviors of RC circuits in the presence of resistors and capacitors, and use multimeters to calculate properties and values of the circuit. The results are the current flowing through the circuit in part 1 is 0.014 amperes, which is different than the original value calculated. Capacitor charge time is roughly equal to capacitor discharge time, which correlates with the equations associated with those values. And calculated values of current and voltage are closely related to the measured values during the experiment using the multimeters. The key concepts, it's a lot to do with physics of circuits. So we have RC circuits, the loop rule, node rule, Ohm's law, steady state circuits, conservation of energy, and conservation of charge, which are all big parts of this lab. Assumptions. Per one, the circuit includes the circuit, the batteries, resistors, and ammeters, and the surroundings include everything else, such as Earth and the air around it. Resistance due to the ammeters is negligible, and there's no resistance in the wire. Methods. So this is the first part of this lab. We construct an RC circuit consisting of two ammeters, two 1.5 volt batteries, which sum to 3 volts in the circuit, and two resistors. The predicted one of 47 ohm and one of 100 ohm resistance. The predicted current and calculated current for both ammeters, or the values of I1 and I2, are 0.0204 amperes, whereas the actual value, as seen on the multimeters, was 0.0148 ammeters, and the reverse reading was the negative of that. The change in voltage, which is measuring the potential differences at various points in the circuit to analyze voltage drops across components. So, using the fact that delta V round trip in the circuit is 0, we were able to produce the graph below and calculate that the 47 ohm resistor had a voltage drop of 0.86 volts, which calculated to 50.588 ohms of resistance. The 100 ohm resistor had a voltage drop of 1.8 volts, and which calculated to 105.88 ohms. The wires had a 0.22 volt voltage drop, which calculated to 12.941 ohms. And ammeters had a 0.05 voltage drop, which calculated to 2.94 ohms. So, as seen, the wires weren't actually didn't have no resistance, like in the assumptions prior, and the actual calculated values for the resistance of the resistors was higher than the predicted or the stated values, likely because of some error in the reading of the ammeters. Methods. The second experiment we did was using charging capacitors, where we had a system of two 1.5 volt batteries, a capacitor, and light bulbs of varying resistance. The 10 ohm bulb charged in 12.8 seconds and discharged in 11.86 seconds. And the 20 ohm bulb charged in 58.49 seconds and discharged in 57.84 seconds, which are very similar and would be expected, as they have similar formulas. Discussion. So what if you charge the capacitor with no resistance in the circuit? Well, in the ideal model, this capacitor would charge instantly, based on the formula as shown to the right. And since RC is on the bottom of the exponent in the formula, if R is 0, V approaches infinity, and so it charges instantly. World application factors like internal resistance of the battery, resistance in the wire, and parasitic elements prevent instantaneous charging because you'll never have an actual resistance of 0. Thanks.